Hello, let's finish up that section on radioactivity. The next two topics are fission and fusion. Okay, nuclear fission is the splitting of a nucleus when it's hit by another particle. And as an example, here's a neutron flying in and striking a really big atom's nucleus. And there's a variety of products, and here's an example of what might happen. You get two large pieces, and then you have three separate neutrons come flying out of there. And the energy that sends them apart is electrostatic, protons here repelling the protons here, but it also has to do with the fact that the nuclear strong force, the force that was holding them together, sort of like a compressed spring. And then when that lets go, because it doesn't operate over long distances, that energy of the force that was holding them together, that's released. And it kicks those little pieces out, the parts of the nucleus. If we put that drawing into chemical terms, the neutron, well, we'll use the symbol N for neutron. And what's the mass of a neutron, mass number? Well, it weighs about as much as a proton, so mass number 1. And then its atomic number of protons, well, there aren't any, 0. And it has 0 charge, so we'll just call the atomic number 0 for a neutron. If you go to the periodic table, U stands for uranium, Ba stands for barium, Kr is krypton, and then we get 3 more neutrons out, and a whole bunch of energy. And it turns out that nuclear fission is a source of energy for nuclear power plants and some of the nuclear bombs. Now let's look at fusion. Nuclear fusion is where you connect or combine two nuclei to form one big one. And so here we have deuterium. Oh, you remember that isotope of hydrogen? It's hydrogen with an extra neutron in there, so it has mass number 2. And then tritium's also an isotope of hydrogen, but there's 2 neutrons in it, so the mass number is 3. Well, we can have those two atoms, deuterium and tritium, collide so that their nucleus fuses together, and then it turns out there'll be an extra neutron that's kicked out, and you end up with a helium atom or helium nucleus with 2 protons and 4 neutrons, and that's really stable. And then, interestingly, a whole bunch of energy comes out. So then the question is, where's that energy coming from? Well, there's no electronic repulsive force inside a hydrogen atom. There's only a single proton. Same for tritium, still hydrogen, just 1 proton. But now, inside the helium nucleus, you do have that electrostatic repulsion. Light charges repel. And of course, the nuclear strong force holds them in place. But it doesn't make any sense, to me at least, that there would be a whole bunch of energy released, like this is a better state. This is more relaxed, more stable. But that's what the experiment says. The extra energy comes flying out. And a huge amount, not just a little bit. So what's going on? Where is that energy coming from? Here's the clue. We can weigh some atoms. So if we look at the helium-4 nucleus, that has 2 protons and 2 neutrons in it. And you can weigh helium-4 with the mass spectrometer. And a real sensitive instrument, we get a very precise number. This 4.002 AMU. And then you can use the same instrument to measure a hydrogen atom with a neutron in it. That's deuterium. And that weight is 2.014 and some other digits. And if you take the weight of 2 deuterium atoms, well, you got 2 protons in there, and you got 2 more neutrons together, 1 neutron in each. You have the same number of particles, but add them together, it's 4.028. What's going on here? Why aren't they weighing the same? Where is that missing mass? Well, we need Einstein's famous equation, E equals mc squared. E is energy, m is mass, and the conversion factor that makes mass equal to energy turns out to be the speed of light squared. So where's that missing mass? It was changed into energy. And it turns out that nuclear fusion is a source of energy in the sun and in stars, as well as a few nuclear bombs, like the hydrogen bomb. Okay, another thing about radioactivity is that there's some randomness associated with it. And what I mean by that is if you have a collection, or scientists call it a sample of radioactive atoms, and make them all the same element, same isotope, so that they're identical. And you put them in a lab and you want to study them, maybe behind some lead shielding to protect yourself from the radioactivity. Well, it turns out they don't all detonate or go radioactive at the same time. That's what's random. It's like, let's say you look at 10 radioactive atoms and you know they're all the same. They're all going to be, releasing radioactivity at some point in time. You can't predict when. All we know is if we study enough of them, on average, we can predict or at least measure the time it takes for half of them to go radioactive and decay. And that measurement is called a half-life. Half-life is the time required for half of the sample to decay. So for example, carbon-14 is 5,730 years. Well, for our calculations, we'll just round off to 6,000 years. So if you have 10 grams of carbon-14 in 6,000 years, about half of those atoms, 5 grams, will have gone radioactive. Phosphorus-32 is also another radioactive isotope, but it has a much shorter half-life. It's about 14 days, 2 weeks. And it goes by the same principle. If you have 10 grams of phosphorus-32, in 2 weeks, half of them, 5 grams, will have release of radioactivity. But another 5 grams, the other half, you still have to wait. There are 2 kinds of half-life questions. Here's an example of each. Sample problem number 1. If there are 8 grams of P32 today, how many grams of P32 will remain after a month? The second type of question is, hey, let's start with the same quantity. 8 grams of P32 today. How long will it take for P32 to decay to 1 gram? And you deal with those questions the same way. Find out what the half-life is. So that's what these sample problems are missing. We have to be told that the half-life of our isotope, in this case, is 2 weeks. So that should be given in the problem. If it's not, ask for that. We're going to start with 8 grams, and you wait one half-life. That's 2 weeks. And the definition of a half-life is the time it takes for half of your starting material to decay. So, of the 8 grams, 4 grams will release their electron out of the nucleus, change into some other element. But 4 grams, the other half, haven't changed yet. So there's still 4 grams of P32 that hasn't yet detonated, hasn't yet changed by radioactivity. So, have we gone a month yet? Nope. We need 2 more weeks. So that altogether, the total time is 1 month. And then what we do for the last half-life is say, okay, we start with 4 grams, wait 2 weeks, so the half of it decays. There's 2 grams left. How many grams remain? 2. Turn around the other way and say, okay, got our P32, 8 grams today. Now you want to wait and see how long it takes for it to decay down to 1 gram. Well, take it through several half-lives till you reach 1 gram. First half-life takes 2 weeks. You get half. Half of 8 is 4. Go another 2 weeks. Half of 4 is 2. Well, we're not at 1 gram yet. 1 more half-life. 2 more weeks. Half of 2 is 1. There we go. There's a match. And the total time it takes is 6 weeks. Okay, last idea. Carbon dating. Sorry, got a little silly picture here. But carbon makes up charcoal, pencil lead, and diamonds. Silly little cartoon. Okay, what are we talking about with carbon dating? Well, that's where you use the radioactive isotope, carbon-14. And you can dig up fossils and measure the remaining carbon-14 in that fossil and use it to predict or estimate how long it's been in the ground. So here's the idea. Cosmic rays, stuff from outer space, strike the atmosphere, and our air, our atmosphere, is over 75%, 76% nitrogen. And sometimes the cosmic rays collide with the nitrogen and change it into carbon-14. And that's happening today, every day. And that's one assumption, that throughout the age of the Earth, this has been happening all the time. And so there's a constant creation of carbon-14. And then carbon-14 is radioactive, but it has a long half-life. It takes 6,000 years for half of it to decay. And then more of it is created in the atmosphere. So on average, there's a constant amount. Okay, where's that carbon-14 end up? Well, it reacts with oxygen in the atmosphere to form carbon dioxide. And that's a nutrient for plants in photosynthesis. And plants take up this special isotope of carbon. Carbon-14 and carbon dioxide turn into sugar. Makes the trees, makes the leaves, elephants, well, a mammoth rather, eats those leaves, uses it as nutrients, and the carbon gets taken up in its body. And at the time that they're living, these plants, these animals, have the same amount, another assumption, of carbon-14 that the atmosphere has. Same ratio. And then, when they die, here we got the tree dying here, well, now they can't do photosynthesis. A dead animal can't eat anymore. They don't take in any more fresh carbon-14. So whatever they have at the moment of death, the assumption is that's the same amount of carbon-14 in the atmosphere. So they have 100% in terms of comparing the atmospheric quantity of carbon-14 to their own bodies, or in this case, the remnants of that tree. It's not that the whole stick is 100% radioactive carbon-14. No, it's just saying that it has the same amount as the atmosphere at the time that it was buried or time of death. Okay, but now it can't acquire any fresh carbon-14 like the atmosphere. So the atmosphere keeps getting regenerated by cosmic rays, so it always has the same amount, 100%, whatever that is. So carbon-12 is the most common form, most common isotope, about 99%. Carbon-13, about 1%, and then carbon-14 is a trace amount. And you might remember that the isotopes of hydrogen follow the same pattern. Okay, so there's a small amount, but whatever that amount is, the atmosphere keeps a steady amount of that. Whereas this object in the ground, age 0, has the same amount, but in time, one half-life, it loses half of that quantity. Second half-life, now it's reduced down to half of 50%, which is 25%. Half of that, another half-life. So what happens is someone will dig this up and measure the quantity of C14 that remains inside the fossil, or this artifact, whatever it might be, and you compare it to today's quantity of C14, and assuming that that hasn't changed over time, you can figure out how many half-lives it's been in the ground. So here it is. In this example, this piece of wood's been buried for 17,000 years. Okay, that's all for now.